for the next hour. There's a panel. We're kind of honored to have Barb Ryan, who is the Executive Director of the World Geospatial Industry Council, who's going to be moderating this panel. The panelists are Matt Shellenberger from American Electric Power, Peter Atalla from Voxel Maps, when we talk about the digital environments for digital twins, and then Craig Stenberg, who's a UAS program manager for Southern California Edison. Welcome, and Barbara, thank you for posting this, and take it away.
Great, Gavin, thank you very much, and thanks to the organizers too. And it was really useful having Dexter's presentation start this up, because I think what you're going to find from the discussion that comes out of this panel is we'll make some linkages back to his presentation. So thank you, Dexter, for that. Again, my name is Barb Ryan, and I'm Executive Director of WGIC. It's a not-for-profit trade association, but you must be a private sector entity working in the geospatial or Earth observation ecosystem to join. So while we're not-for-profit, the membership are private companies, and I'm happy to say that Peter and Voxel Maps is one of those members. So thank you, Peter. Listen, I do have just one slide, and so I'm wondering if that's available and we can just put this up, and I can do it at the end also if it's not available. I just want to draw attention that we take on a policy topic every year, and Dexter also mentioned AI in his presentation, and that was our geospatial AI was our topic last year. That report is available on our website. But this year it is in fact digital twins. So this is just a call to anyone listening in that if you are researching, involved in, or developing, or currently using digital twins, we would love to have you complete this survey. It takes about 15 or 20 minutes. It's shown on that slide. And then if you have a particular interest, certainly for those WGIC members, we'd like to follow it up with some interviews that would take a little bit longer. So thank you for that slide. Okay, now we'll go back. Listen, if you saw the description for this panel session, I think it's just really important because once the purview of the manufacturing sector, these digital twins are increasingly being developed and used in the built and natural environment. And so I think what will come out of this session is, well, first of all, whether it's digital twins, whether it's the mirrored world, whether it's the metaverse, there's a lot of different ways we can characterize this whole environment. But I think what I'm so excited about with this next panel session is that we're going to see it, either it or the lack thereof, in a real life situation. So we'll do a couple different things. We'll start up, I guess what I would say is kind of at the national level, Matt, with you going first from an American Electric Power perspective. We'll then come down spatially a little bit to Craig for the Southern California Edison perspective. And then we'll end up with Peter, who will talk just a lot about all the data issues that I think many were teed up in Dexter's presentation. And then we'll open it up for panel discussion. So I'm expecting a couple minutes and probably some slides from each one of the presenters. Talk about your domain. We'll just plow right through one, the other, and then we'll field questions. And just a notice to all the audience that if you have questions as they go along, feel free to post them as you think about them, and we'll try our best to kind of keep track of that. So, Matt, would you like to start, and the rest of us can turn off our videos so that we're focused on you?
So I just have 3 slides here just showing some of the things we've been doing with digital twins. So the first one here, I'll describe how it was derived and then how it's being used. So This is the original derivation of the model was a transmission line design tool, PLS CAD. Most people are probably familiar with that. And that was augmented with LiDAR flights on, we did 7,000 miles of our extra high voltage circuits across AEP. We're in 11 states, so lots of room for EHV. I believe this is a 345 line. And so that LiDAR was used to then double check the design in PLS CAD and produce a 3D model with what looks like spaghetti up there. There aren't that many conductors up there, but these are the different sag and some people call it sway. I tend to call it blowout models of the wind being subjected onto the conductor. So this is being displayed in an augmented reality tool from Trimble called Sight Vision on a mobile viewing device in the field. And primary use here is to help the forester that's maybe talking to a customer or just out checking the impact of trees along the right-of-way corridor and making sure that we have good clearance under the design conditions, which are not readily viewable on a nice 70-degree day with very little wind. So this allows the forester or the customer to understand maybe why we need to trim a tree that looks on a non-windy normal day as not being an issue. So along with that, so that's kind of the upper left picture. The lower right picture is really showing another tool in this augmented reality application that you can show edge of right-of-way and help customers to understand, or people coming out to do physical work trimming, understand where the edge of the right-of-way is and what is in or outside of that that right-of-way. So this is kind of a sheer vertical wall that you visualize in the tool, and it helps people to understand where that edge of the right-of-way is. So my second diagram is more around constructability and then also thinking out further for as-built comparison to see if what was designed is actually what was built in the field. So what this is from is our distribution design tool, so GSI's Distribution Design Studio, and this is a tool that we're upgrading to allow the creation of these 3D models. The 3D model would be automatically created based on the user's design. It would be posted to a web service through the cloud, and then made available for various stakeholders, whether those are customers in the field to see, again, kind of in that Trimble Sight Vision type use, or just in the office looking at the design and giving feedback. So on this little call out, you can see that the guy wire, the kind of teal colored wire, is going right through the middle of a transformer. Well, that's not going to work, obviously. So the person reviewing is able to come in here and put notes on top of the 3D model, share that back with the designer, and so that they can make adjustments to the design. The longer term idea here is to make this 3D model photorealistic enough so that when we do go after the fact and scan the as-built, whether that's with LiDAR or with camera systems mounted on a truck, mobile mapping, that we can compare the as-designed to the as-built and see if the two match up. So that's another concept with digital twin that we're looking at. And then lastly, for our downtown electrical networks, the things that some people walk across, I don't necessarily tend to. So these are vaults and manholes in our downtown network, and this is an example of a scan that was done in one of those manholes. No equipment other than cables in this one, so it's a manhole versus a vault. But being able to then measure off of this LiDAR or laser scan that's been colorized within the tool. So in this case, using a laser scanner, we're looking at various options here. This is still a little bit early in development, but this is very useful for both the physical folks that might have to go back down into this vault, or for the engineering folks that try to figure out what options are available to them and what can make it into this manhole and what maybe can't. So just kind of a short overview of some of the things that we're doing in the digital digital twin world. Thank you.
Great. Yeah, thank you very much. I'll tell you, I don't go out of my way to avoid those manhole covers. So after that slide that kind of looks like a bat cave and your guidance, maybe I'll do so in the future. Also, I'd like to say that Trimble is also a WGIC member, so glad you're working with them. Okay, Craig, let's go over to you for Southern California Edison's perspective.
Thank you, Barbara. Good morning, everybody, or afternoon, as the case may be. I guess some may even be evening. Anyway, so I'm Craig Stenberg with Southern California Edison, and I'm happy to be here. And I've kind of shortened the presentation down a little bit, just for the time that we have. So I was going to talk a little bit about the digital twin methods that we're just now finally launching into. We've had a LiDAR program on the books for about 10 years, and it's finally becoming a reality this year. So talk about a little bit why we do the things we're doing, and then move on into how we process that data. So first, you look at LiDAR, and this is, I believe Matt had a much better image here. I was not allowed to bring company data into this presentation. I didn't get that approval, so I apologize for that. So anyway, what I can present to you on, though, is how do you get to this point if you're starting a program on your own at this point. So what the LiDAR is doing, for those who may not know, is it's basically it's a radar with lasers, and you're creating little tiny points. So you're creating a Monet painting, really, in 3 dimensions. A whole bunch of little points that make the big picture, no pun intended. And another technique that you can use is something called 3D photogrammetry, which is something Matt had also touched on a little bit. This is one I did quickly with using a drone. This is actually my house, and the processing power that was behind it wasn't as robust as some of the ones you do see in the industry, and I'll get to that a little bit later on. Part of the reason that this has some of that kind of Picasso-esque looking features is because this was literally almost a randomized shoot. All these little blue points are places where the aircraft was at every photo. So by using a series of photos, you get in what's called 3D photogrammetry, where the software does the complex mathematics to create the 3D image using various points in the photo. If we look at these roof points that all come to a point, every one of those viewed from a different angle is going to have a different look. And what the computer is doing is taking all these points in the photos and saying, the only way I can solve this solution is if this thing has this shape to it. And that's how we get to this. And moving on to this, some work we did do for one of our groups in the company who is looking at some of the solar fields that we purchase power from. So just I wanted to bring in at least an actual industry example of what's going on here. This is using Esri. We actually use Esri drone to map to do the initial structuring out of this, and then imported that directly into ArcGIS. I know Esri was mentioned earlier in this call, so I know that most people work in the utility industry. If you're in this field, you probably have heard of Esri at some point. So again, these are the points where the aircraft was, much more structured flight path. And this was actually constructed out of 3 different paths where the camera is at nadir looking straight down, and then 2 paths where the camera is looking at left and right at a 45-degree angle. So the more photos you can put in, usually the better your product is going to be. This is what it looks like if we get rid of those points in space. So now the other thing you can do with this, however, is create a 2-dimensional representation. And the reason I put this up here was to point out these features here that look like they're imperfections are actually the terrain over which it's flying. So what we're able to see in this 2D representation of the 3D photogrammetry is that we're starting to mimic the product that's going to come out of a LiDAR system. There are limitations, though, I'll talk to you about in a little bit. The beauty of having both the LiDAR and the 3D photogrammetry, however, is the synergy of the data. And you don't have to stop at 3D photogrammetry. Any kind of imaging that you can assign to specific geospatial points can be synergized and used in this way. That's what makes this so powerful. So straight off of the aircraft, your LiDAR data will look more like this, you see in the top section. Once you fuse that, and Matt had a good example of that in his underground vault, you've colorized the photo. You basically take all the pixel information in the photo and assign it to the point clouds from the LiDAR and literally create a three-dimensional photograph out of your data. Now, this can be put on a desktop and moved around in real time by somebody who's using this data, consuming this data to make decisions out in the field. It's especially helpful for work planning. If you're going to build a new circuit someplace, you can get a bare earth model out of this and see what it looks like without all the vegetation. So, so your as build is your first real big, I guess, product or benefit you're getting from this. This is when you're going to do your baseline scan. The first time you do your scan, you're going to get all these different things, and finally, you have your tower integrity baseline topographic. You have real property evaluations you can do, and it all leads to early compliance actions. Now, the real property evaluation, the reason that's important is when you get to your future settings, what has changed? Now, you may you go through, you do this other scan, and you're starting to find things that are different that weren't in the last scan. That's why that baseline is important. And in your real property, that's where you made we've actually found people that have marijuana grows in our right of way and things like that, or people have built curious structures in there that don't belong. Perhaps you have people stealing your power or something of that nature. But the other piece is your change detection is in your vegetation management. It's in your structural shifting, your topographic shifting, and you may be saying, well, the Earth doesn't really move. Well, we're in Southern California. The Earth does move here. So that's the LiDAR is probably the best tool to determine these minor changes that occur that are actually calling out much larger problems in your structures. There's our past benefit to LiDAR. Well, if you live in California, archaeological finds are a big deal, and that all becomes part of that environmental concern that you have. So that first picture I showed you there was showing a photograph of an area that's now represented by this LiDAR scan. And this is a LiDAR scan of some actually ancient Mexican or ancient Mayan structures that were found in Mexico using LiDAR, found inside of the vegetation. So if you have a utility that you're doing where you're going to do some work and you go and do your plot to build a new circuit and everything else, you may want to go back and from your LiDAR data and make sure you don't have anything like this that you're going to find in your way, because that will actually shut down your construction in most places. So moving on to the flow of this, you have the hardware side and then find the software side. And I think someone else is going to present on this in more detail. So I'm just using this. The reason I approach this part is many people get tied up on how do I collect this data, then they don't think about what it's going to take to consume the data, to process the data, and finally to store that data. So your data collection is the first step. It's all hardware based. It's the equipment that you have. It has the lighter application of the computers on that side, because most of the time the data collection systems are going to be doing most of that work. Moving into data correction, you're starting to get into that the software piece where you're correcting your data, aligning it, taking out the errors that happen during collection. So more software is being involved. If I get into feature coding, that's where you're going to have the heaviest hitting software and creating that three-dimensional image out of that point cloud. And finally, where you have the largest consumption of electronics and computer power as well as software is in that AI and machine learning. And when I first joined, the gentleman who's presenting, I'm sorry, I didn't catch your name, but you're one of my colleagues in the industry, so it's really embarrassing. had a good representation on what that AI is about and everything else. So with what you're collecting, that's ultimately where you're going. You're looking for that data that's going to seek the user. Where right now, the current model is you go out, you're looking for problems by scanning through all this data. So that's the user seeking the data. When you have the data seeking the user, you have that powerful system where the computer is already finding flags in your data, things that may be causing issues. And that's what the AI and machine learning is leaning towards. This is just some video cards. The reason I'm showing up GPUs is that's where most of that information is going to be crunched, in that GPU system. That you really you're building that system around a GPU structure to really utilize, turn that system into that supercomputer. So finally, let's get into your large server storage area. I'm sorry, that's not the right server storage. Here we are. Okay. Your laptop is not going to cut most of this stuff. You're going to have some very serious power to crunch this data. Most of these softwares are working off of applications such as Bentley Microsystems, and these all take larger desktop workstation types. But if you're a larger utility, you may want to look at building the GPU-based server within your actual data center, where people can subscribe to services, and overnight you can do really heavy lifting on crunching this data to create that digital twin. So this is what I have. Just giving a quick overview on how you build that program out within your departments and within your utility. So if you got any questions, we do have quite a bit that we've been doing at Edison. I just unfortunately wasn't allowed to present a lot of it right here, but I'm happy to answer. I can answer your questions about it all day long. So
Great, Craig. Thanks. Thanks for that. You might have to stop sharing.
Okay, look at that.
Great, good. Yeah, Craig, thanks. Nice job on that. And also there were, well, at least one comment in the chat box as we were working. The visualization of that is just so important. You know, we live in a 3D, 4D world. We don't live in a 2D world. And so the more that, the more that we can visualize, the more that we can make the virtual world look like our real world, the better off we are. And so there was a comment to that effect. So thanks for that. Also, I will add that Esri is a WGIC member. In fact, Jack Dangerman chairs our patron board. So again, thanks for the call out to another member. Listen, let's go to the third presenter in this panel. That's Peter Atalla, CEO and founder of Voxel Maps. And I can tell you, Peter, you know this, I am really excited about the vision that you guys have. I've worked in the field for 40 years, and yet I still feel like I haven't had anyone that characterizes the importance of voxels in just 3D representations from the center of the earth right through all the way up that are scalable. So I'm just really looking forward to your presentation, and I hope folks on the line are too. So over to you, Peter.
Brilliant. Thank you, Barb. Really, really appreciate that. Let me just share my screen. So good morning, everybody. I hope you can see my screen okay. I've just got a few slides today just to kind of introduce what we do at Voxel Maps and how it also relates to digital twins in particular and utilities. And great presentation by both Matt and Craig. And actually, Craig, what was really interesting, he brought up that archaeological example. And we were actually involved in some of those things, not the same one, but also in Mexico as well, looking at the foliage penetration properties of LiDAR and then modeling all of that as well. So completely different use case, but very, very interesting. So everything we do at Voxel Maps is really around this concept of building maps for machines. And underlying that, what we're really building is a digital twin, but not just a digital twin, as maybe a lot of you have heard about. There's a few kind of buzzwords which are really important here. Firstly, it's 4D, so it's 4-dimensional. We've got a time dimension component to it, which is really interesting for change detection, and it's volumetric. And I'll come on and I'll explain what I mean by both of those things. So firstly, what do I mean by machine maps versus human maps? So human maps we're all pretty used to. These are the maps in our phones, in our cars, on our computer. And really they're designed around two sort of use cases. One, navigating people to an address, which could be a street or a building or a city. The other use case is really displaying geodata, so kind of creating layers of geodata. The majority of human maps are 2D. There are some 3D elements, but it's not extensive yet. And it's pretty low resolution stuff. So 1 to 3 meters is typically what we see with the traditional human maps. And the majority of the use case is outdoor. We're starting to see some indoor use cases, but again, the big application is being outdoor. So if we contrast that to machine maps, these are very different. Firstly, we're talking about true 3D and 4D spatial models. So absolutely everything we can see in a given environment. So it's not just about the roads or the buildings or the land classification. We're looking at every object that we can see. So infrastructure, telecoms, utilities, vegetations, land classification, and structures as well. We're doing this at very high resolutions. So 1 to 4 centimeters is typically what we work at the moment. And at that resolution, it's not just about the location of the objects, but also about measurements, attributes, sub-features of the objects as well, which become really important. So then when we talk about machines, we're really talking about machines from AI models or different computer models to better understand a given environment or infrastructure, all the way through to new forms of autonomy, whether that's autonomous cars or drones or AMRs, automated miniature robots, for example. And so there's a requirement for the data to be everywhere, outdoor, indoor, subterranean, everywhere you can think of, we want to grade it. So the approach we take is different from a standard 3D approach. We use something called a volumetric approach. So just giving an example of how that's different to 3D data. So this is an example of a 3D map. This is from Google, but there's similar products from Apple, from here, many other providers. And this is a great tool for human visualization. It really is 3D. It's a great representation of the city. But when you actually delve down into it, you see it's a very low resolution structure. So these structures are kind of meshes with some kind of texture that's put around it to try and make it look photorealistic for visualization. But you wouldn't want to perform any calculations of this. There just isn't enough information. Also, there's no interior information in the model. It's just an empty mesh. If we were to go inside, there's nothing around it. And that's one of the problems with meshes. Meshes really came from computer gaming, and they're really only focused on one aspect of physical matter, which is the surface information. But if interior information is important as well, then they don't really cater very well. Also, meshes are relativistic frames. So even if you were to go and scan the inside of this building, you couldn't fit that internal scan into that existing mesh. You'd have to destroy both and recreate them together as well. So the approach we take is very different. It's volumetric. So we're using voxels, which I'll explain what voxels are. But essentially what it means is we can both map the exteriors of buildings, of infrastructure, plus interior information in the same model at any point in time. And that information automatically just drops in. It doesn't need a lot of human involvement, post-processing, all that kind of stuff. And we're combining that then with this fourth dimension of time, which gives us this ability to do change detection. So the way that we do this is using voxels. And voxels aren't new. They've been around for quite a while. A voxel is just a 3D pixel. It's a cube, essentially. And so voxels were first used in computer gaming. Minecraft is an example of that. But actually, we started using voxels in a different configuration, something called a VOG, a Voxel Occupancy Grid. And this was research that really came out of robotics. And so typically the use case in robotics would be that you would have a small robot with some form of 3D scanner. It would go into a room, it would produce a very basic 3D occupancy grid of the room so it can navigate its way around. So we took that concept, but we applied it essentially to the entire planet. So it's an area of technology called an MRVOG, a multi-resolutional voxel occupancy grid. So we took the Earth, we placed a giant megavoxel on the top of the Earth, and then that megavoxel goes straight through the planet. It's an Earth-centered, Earth-fixed reference frame. So it goes from the Earth all the way through. And it's comprised then of multi-resolutional voxels, which theoretically can be absolutely any size. Typically, we use 8-meter voxels that currently down to 1 centimeter. So each of these voxels has a unique position in space and has a unique address, a machine address. But to start with, it's just blank. There's no information in it. It's just a 3D, 4D georeferencing system. So what we do is we validate the occupancy status of the voxel. Basically, is it free space or is there something in it? So we do this using LiDAR. So if the laser from the LiDAR passes through a voxel and it's not reflected off anything, then this is free space. But the moment it's reflected off a surface, we label this as occupied. And so essentially what we're doing here is we're etching out the matter of the planet. But we do this in a probabilistic way. And so there's a lot of clever processes that we can take to make this exceptionally efficient, to solve a lot of the merger problems and noise problems that actually happen when you're just dealing with, points by themselves. But really at the core, what we've created is this global spatial database for this 3D and 4D data. And it really is designed to be planetary scale. So it's persistent, meaning it's always on. We don't view 3D data just as some files you put into a view or an application for analysis. You can actually do planetary level, country level, state level analysis over it. So it's designed to scale to thousands of petabytes. We have private clouds where Greg was talking. We have many servers with multiple, hundreds and hundreds of graphics cards, which are actually do all the hard work of processing all of this information as well. So using this approach becomes far superior than using just points or meshes. And I just want to kind of explain that a little bit. So points are fine. Let me go back a moment. So points are good, but they're very unstructured information. So it's quite complex to process them, particularly if you've got multiple passes on a particular area and you're having to try and merge those points. And over time doing it becomes even more complicated. So most people end up doing some kind of processing and then kind of archiving off the raw points, not really kind of touching them too much again, and becomes kind of a storage solution for them. Other folk change that into meshes, and meshes, they're definitely structured. So that's a big benefit as opposed to points. But these are, as we've discussed, quite low accuracy models, and you have no ability to update, certainly not incremental updates. You have to kind of recreate data sets each time you do it. But voxels really kind of sit in the middle of all of this. They're structured, but they allow for real-time incremental updates. So you can just change parts of the data and update them as well. Real-time, we've done projects actually recently as public information with Verizon, where we're using 5G connections and offloading data in real time, and around 15 seconds later, processing all of it, all the analytics, the processing done as well. But most importantly, from voxels, you can convert back to points or you can convert to meshes as well. So it's this perfect area to build a digital twin, a living, breathing digital twin that you can kind of update. So just some very quick use cases. It's entirely integrated with AI and ML, and it does this in 3D and 2D. So it's a 3D semantic segmentation, not just a 2D image with some LiDAR points overlaid. We're really looking at objects in 3D. So we have examples of infrastructure asset management, of vegetation management, and vegetation prediction as well. We also take advantage with vegetation of some of the properties of foliage penetration from LiDAR. We can actually see some of the infrastructure. We've got a dense enough point cloud through the vegetation as well, which is very interesting. Things like joint use audits are important. And a key aspect of that is the change detection. So we can actually look at assets that have changed over time, and we can flag that up to people or to inspectors to go and have a look. Was it installed in the right place, for example, in a joint use case, or if there's been a problem with a particular line, for example, or you have a defect, flagging up those kind of defects as well. And then things like power line classification as well. It's all possible from this. So it's a complete digital twin model that can live and breathe. So as you collect data, it will ingest more data over time. And then you have the ability to power it and do all of this automated extraction with AI and ML as well. So that's a quick overview in terms of what we do.
Great. Thank you very much, Peter. I think we can stop sharing your screen, and we'll ask everybody to come back online to start the question and answer period. And let's see, there are a couple. Well, first of all, just thanks everybody. Before I dive into the questions that are on the screen, let's see, Craig or Matt, first of all, you have any questions for Peter? Because I imagine that's maybe the first time that you've seen his presentation. And I know that, well, for example, Craig, you were talking about how landscape changes in California you know, and then Peter did talk about versioning, I guess. I didn't know if you had a follow-up question for him on that point or any other. And of course, Matt will offer an opportunity to talk for you to ask any questions as well. And then I'll dive into the questions in the chat box.
Thank you, Barbara. Well, first, Peter has a great presentation, very impressive treatment of the data. So something I'd not seen before. So I'll be following up with you offline on some more of that as we continue developing our programs. But you did mention change detection on that. What I guess what is the greatest application you've seen in that so far? As have you done any real utility change detection at this point, like tower structures, things like that?
Yeah, no, great question. So change detection, I suppose, is the hottest area that we're developing really at the moment, and it's the one, I suppose, that has the most value. You know, when we're talking to potential customers, they're very interested in detecting change. So the biggest applications we've had so far is really about city infrastructure. And so very often, with the deployment of things like 5G, the small cells, you're having this kind of joint use case where, you have one party that might own the infrastructure, but they're leasing out, they've sold the space to a telco, and, units are being installed. And so there's this whole kind of compliance, part that comes with that. And all of that can be automated and actually in a better way than normally manual surveys, better data, faster, etc. The other thing that we've started doing in utilities is where we have defects. And I would say it's still early days for us on the 4D. So it's really interesting, actually, what Matt was talking about as well, and the kind of data that's potentially available, there. But definitely each of the voxels, without getting into the model too much, but have an infinite number of time states. So the more data you collect over time, the more you kind of slot in those point clouds and convert them to voxels, the more of this data you can use to kind of see the change between them. And the system can be intelligent to the point that it's trained to tell you what has changed, or it can tell you there's just been a change. It might be something it hasn't learned, but it sees something's off, something's been added, something's grown, something, shouldn't be there, and it can alert you to it as well. So we kind of have a process of, we train it ourselves to kind of cover off the major use cases. But we also have a full training suite. So different customers kind of take it from us. They do their own training and they run their own, networks as well over the data that they're building. So it's so still, to answer your question, a lot more that we need to do, but some really good initial use cases for it.
Thank you. No, it sounds very exciting, actually. And so you mentioned, it's building out data. Let's say from a typical point cloud data set, what would the end use, or I should the end state data consumption look like on Voxel Maps from the initial point cloud it came from? Like what number X increase in data are you looking at for that?
In terms of the data size, increasing the data size, yeah. It's a marginal increase. I mean, where you really do get the bigger increase is where you're layering on metadata. So for example, imagery can be metadata associated with the voxels or the 3D objects, and you're pulling that back. And as and Matt was talking about this can be very big data, right? So you kind of got to think how you offload and what you do. But we ingest point clouds from all sources. So sometimes it's UAV, or it can be aerial with helicopter. It can be ground-based, both cars and people walking around. We then voxelize that data set. All of that processing is kind of done in our kind of private cloud. And then the classification, happens on top of it. And then you have full access to the data. So you can visualize, it's kind of like a 3D game. You can go around it, or you can export it out into any of the applications that you would typically use for asset management or handling this kind of information.
Thank you. As you may guess, that becomes probably one of the more limiting factors in this technology is when you start building your data sets, you start finding that where am I going to put all this data now? And
exactly.
You really cannot underestimate the size of the server that you need to sort of the cloud, I should say.
100%. And that becomes a huge problem. Just one, where do you store it? But also what we see happens with customers is the older data sets kind of get ignored, right? Or it's such a big challenge to kind of, have a data set from a year ago and see kind of how it relates to the latest data set that, points aren't ideal for keeping that data persistent and being able to do analysis on it in real time. And so that's why we kind of say, well, this Voxel model becomes a home for this kind of data, which can become useful, not just a storage, solution.
Well, I said, well, I'll be in touch.
Great.
So,
Matt, anything from your perspective before I turn to the Q&A box?
I mean, I've had a little bit of a introduction by Brian Soliday a month or so ago, so I had a little bit of time to think about it. The example of the manhole vault, one of the things that we do there is we turn that into like a 3D wireframe or then a solid object. So do you see converting from more or less that point cloud scan to a voxel, alleviating the need to turn that into a 3D solid? Do the voxels give you the ability to more or less to create a brick wall almost, if you think of it that way, you know what I mean? Versus having to create that 3D wireframe model that becomes a solid.
Absolutely. You don't need to go that step unless you want to. And there are some use cases where that's still useful, for you. So the voxel model, because it goes through everything, where you're sat now is full of these imaginary, virtual voxels. Mm-hmm. So we can model interior spaces, in the same ways we model the exterior and subterranean spaces as well. So it all kind of exists within this global reference framework. And importantly, because you've got this update capability, this incremental update, it's much better than converting that then to some kind of basic vector objects, which can be useful. Here's where vector objects are useful. They're a very low data footprint. So if you've got applications where you just want to send a small amount of data, then yes, vector objects make sense. Or if you want to create a visualization and have like a photorealistic texture, then that makes sense as well. It's good to use them. But the voxels can convert into that, right? Whereas if you kind of go just points to meshes, you lose that step. You can kind of convert back to points, but it's messy and you lose a lot of information. So it's kind of that in-between space, and it depends on the application, really.
I mean, one of the things that obviously you can't do with just a light scanner is then determine how thick the wall of said, box is. But if we know the general thickness of the wall, can that be used to more or less extend the voxels into some sort of model that represents how thick the walls of that vault are?
Yeah.
You know what I mean? Almost to interpolate it out.
So with buildings, definitely you can do wall thickness if you can get around the whole building. So very often we map the outside of the building and we go inside. And once you've done all the interior walls, yes, you may have some
kind of get that
walls that you can't get to the other side of, in which case you don't. For the subterranean, it is harder. It is harder. You'd have to make some kind of estimates there, really.
Right. Okay. No, that was interesting. I was thinking through some of that.
The use cases,
okay. All right, let me just jump in on that last point, and then Peter, there are going to be a fair number of questions in the chat box for you. But when if the voxels are in fact Earth-centered, so if the reference frame is to the center of the Earth, then what's the limitation on why is it more challenging to do subterranean work? Is it because our sensors are limited in that regard?
Yeah, pretty much. So it's about resolution. Now, one of the great things with the voxel model that we've proposed is it's a multi-resolutional model. So we can take much coarser data or even much more accurate data, and within the same data model, we can represent it. And so really, when we're looking at subterranean, if there are tunnels or structures, as Matt showed, you can take a high resolution handheld LiDAR down and scan it at a great resolution. In other scenarios, if you're using things like ground penetrating radar, you're not going to get high resolution, and so certain other data sets still can be modeled, but it's going to be much coarser, kind of data there, really. So the subterranean world is still the hardest use case, really, to kind of get data, and that's more down to the scanner. If there were future scanners that could do it, we can model it, really.
Okay.
Yeah, we actually tried that out recently with one of the newer on the market scanners that GPR scanners that changes its frequency, right, to try to get deeper down into the earth. And we took it to an area that was heavily clayed, and we still could only get about 2 feet into the surface.
Yeah, it's still a problem. Yeah, unfortunately.
Okay, one more question, but what if it weren't electromagnetic signals? What if it was this is sand, this is clay, this is swamp, you know, what if it were the actual data for the actual substrate?
You could model it. So again, we have situations where we take actually traditional kind of 3D, more kind of vector data, and we actually integrate that in with the high resolution voxel data set. And so, for a particular client, they'd already mapped a city, but it was all in kind of a traditional 3D format. And then they just had kind of a high resolution base. They kind of done mobile collect, very high resolution, which was voxels. And then above it, to kind of complete the buildings, was low resolution data. So it's possible to merge those kind of data sets together, definitely.
Okay. All right, thanks. All right. Hey, folks in the audience have been real patient. So let me just, because a fair number for you, Peter, I'm just going to read them off and you can kind of weave your answer. How user-friendly is it? So you're saying continuous updating can explain your continuous updating. This is from Kevin Foe. How many pulses does your LiDAR have and what are its specifications? I would love to come back to a question that's what can we do with an application of weather prediction? I spent some time with WMO, and so as we go above the earth, I think this is going to be kind of a phenomenal application. And then how does this play into structural analysis like pole loading? I don't know that, so I hope you do. And to be clear, can you import, process, analyze, voxelize other imagery, not just your LiDAR? And actually, I think that was my question. Can you bring soils data in? Can you bring geologic data in? Anything that's below the earth? And then not being able to store data is great. So moving data information through the cloud would be great. Let's stop there because they're coming in fast. So let's stop there and then I'll come back to you. I'll catch up. Okay.
Okay. So let me try and answer a few of those. So it is very user friendly. It kind of does depend on the use case though. So say, for example, if you want to annotate your own AI ML networks to go and do the categorization, there's a process to do that. And really the quality of how you annotate in the beginning will determine how accurate those networks are. So generally speaking, we do that for clients, or we provide training. And I would say that's the complicated bit. The rest is relatively straightforward. With respect to the hardware and specification, we're agnostic from LiDAR sensors. So you don't have to use our own scanners. We have our own mobile mapping for vehicles, which is using 2 Velodyne LiDARs. So we're getting very dense point clouds really from that, plus imagery, plus edge processing and IMU. But if you have your own LiDAR that you've already collected or sensors you've invested in, no problem. We need to know some parameters, but we can take that information and kind of merge it in as well. The continuous updating. So this isn't available everywhere, but what we're doing actually in the US is we're currently putting, for the road network anyway, we're putting a much smaller LiDAR device plus camera device on existing fleet vehicles. There'll be about 2,000 of them deployed towards the end of next year. Which are 5G enabled and always on. And so they're always kind of collecting this information and sending it in real time or near to real time back to us. And that's really interesting data because then we have this real time component and this temporal component that we can start to really look at change detection. For utility corridors, it's a little bit harder, right? Because it will depend on the frequency that you're collecting or we're flying as well. So it's for that use case, it's harder to do true real time, but you can have a very high frequency of updates as well. Quickly, weather prediction. So weather's an interesting one. There's still a lot we've got to do with what we call transient voxels. So voxels that essentially have moving information inside and out of them as well. Weather is one of that. Emissions is one. We even have a project where we're looking at ocean mapping. We're not doing the ocean mapping, but they're providing the data, we model it. And then they create these larger voxels, almost like megavoxels, in the ocean, and they monitor for different DNA samples in there, and they're kind of doing a biological analysis, and this is transient information. So it kind of sits there in a voxel, but it's almost like a metadata component. But that's kind of future stuff, right? So it's very early days, but hopefully next year we'll have some projects that we'll be able to demo with this kind of transient information.
Okay. And then just to be clear, importing other kinds of data. You want to come back to that one more time?
Sure.
Yep.
Yeah, absolutely. So two aspects. If it's 3D data, that's very easy to do, even if it's standard 3D models, that that's not a problem. If it's 2D data, we normally need an anchor point, right? So we need some parameters to anchor it in 3D space. So one example of that is taking, say, Earth observation data from NASA or the Sentinel program, for example, the majority of which is obviously 2D data, but then we're using high resolution aerial LiDAR scans and merging that together, kind of giving a 3D component to that 2D data set as well. And so that's fine. You can have 2D data which is just connected to a 3D voxel as a metadata source, but if you can link it, then you can kind of almost create this new form of 3D data if it's available.
Just real quickly, pole loading in the cloud.
So pole loading, I have to confess, I'm not an expert on pole loading. We have a whole department which looks at this as well, so I will ask that question. I would imagine we can do it, but let me come back to you as well. Yeah.
All right. And I think people would have your contact information somewhere so that they could follow up with a specific question on that. Okay.
Yeah, sure. I'll put it in the chat as well.
Okay. Just real quickly back to the weather issue and actually emission monitoring as well. You know, we just issued a report on greenhouse gas monitoring from space. So those satellite companies that are collecting data from space, public sector and private sector. And so as soon as that transient technological improvement comes through, that'll be immense. Because even on the weather prediction side, I think just those modelers being able to monitor clouds and soil moisture, you know, in those, I'm not soil moisture, but cloud moisture, atmospheric moisture is so important. That's one of the last unknowns, I think, in some of their work. So that would be good. Let's see, I would like to go over, Craig, when we had our we've still got a little time. Craig, when we had our pre-meeting, you really spoke quite articulately to some of the challenges that we have here in the United States, just from a grid perspective. You want to just editorialize on that a little bit, because I think as we move toward this mirrored world, some of those issues that you're talking about could be facilitated. So sorry to put you on the spot, but I was really struck by some of your views when we had the pre-call.
Thank you. If you could indulge me and remind me what we were talking about at that particular moment.
Well, that our entire network, based on states and individual regional grids, hasn't evolved. It's a network that was designed, I don't know, I'm making this up, turn of the century, and we're still largely constrained by that infrastructure.
This is true. Actually, it goes before the turn of the century. So Southern California Edison, for instance, is the very seeds of the company were planted almost 150 years ago. I think maybe it's about 140, 145, something like that right now. So we're pretty old. We've and when you think about going back to that time, the idea of moving this new thing called electricity to over distances to other people, and at the time it was a luxury item. Now it is a necessity for society. That was a pretty heady thing to be able to pull off. Well, you fast forward to today, it's actually one of the few things that haven't really been evolved much beyond where it started. We're still sending power over long distance transmission lines. We're interconnected with each other. That whole AC system runs at 60 hertz. So we all have to be in step with each other. So it's, am I kind of going the direction that we were talking about at the time?
Yeah, absolutely.
Okay.
Yeah, no, absolutely. Yep.
Right. So there's a vulnerability there that kind of makes us dependent on each other to keep this grid flowing, smoothly. So.
And Matt, I wondered if you had any views on that. And then lastly, not familiar with the details of the infrastructure package that's approved, the bill, but is there a large component for utilities?
Well, I know there's a large component, and to Craig's point, you know, we are interconnected, but we're asynchronously interconnected in certain parts of the country because we have a eastern interconnect, a western interconnect, and then we have Texas. And Texas is asynchronously connected to the eastern interconnect, and that was actually one of the problems during the last year's bad events in Texas with lack of generation. And there was an article the other day talking about gas supply and how the two played against each other and kind of fought each other almost in being able to keep some of the generation up and running. So from that aspect, the systems do interconnect, but they don't necessarily interconnect in such a way and with enough volume to be able to offset some of those problems. But I would say one of the things that I've been thinking about from the infrastructure bill is really the broadband to the rural areas, because that impacts distribution quite a bit, because they tend to want to put those cable and telecom facilities on our distribution poles because we are right there next to people's houses, right? So that you can get broadband to the middle of nowhere, if you will. And so we actually have a project like that in Grayson County, Virginia, as kind of a starting project. And so one of the ways that we had considered collecting the as is or, you know, existing is with LiDAR, and then to look at it for what could be added, what couldn't be added without additional what we call make-ready work on those facilities to allow for space or strength in those poles and facilities. So that's where I see a lot of possibly development as well, at least at the distribution side of things, is helping to make that use of the money more efficient by collecting the data so we can do the engineering analysis effectively and efficiently.
Yeah. You know, building on that a little bit, your as is to be, I could envision that if it were a mirrored world for, I mean, you know, a digital twin for the entire United States utility system, we could show some of the flaws that exist now in our current construct, and this might actually drive toward innovation and a much more integrated system.
Yeah, absolutely. You know, the distribution system, like as a comparison, we have 40,000 miles of transmission at AEP. We have 250,000 miles of distribution at AEP. So you can see the scale difference between transmission and distribution.
Okay, all right. Peter, there was one last question I missed. I apologize for this. How can Voxel technology be implemented with, or is it being implemented with any of the existing technologies that might be offered by other companies, Esri, Bentley, you know, some of those? And as you answer that, why don't you go right into any closing remarks that you have, and then I'll turn to Craig and Matt, because I'm sure Gavin is looking at us to kind of wrap up in the next couple of minutes.
Yeah, so that's a great question. And it's a big focus for us in the first part of next year is about the integration piece. We very much want to be a system that is linked by APIs and common formats. So it's very easy to take the data from Voxel and use it in Esri, Bentley, Autodesk, whatever applications that you're using. We don't want to necessarily have to rewrite everything in terms of the workflow of what people are used to. That's not the goal at all. I think the exciting thing for us and for this future technology is, look, the planet is being virtualized. It's going to happen, you know, with everything we're talking about with the metaverse and everything that Facebook is doing. But reality capture and this explosion of 3D data is real, and it needs a home. And that's what we're focused on. So we can't map everything, but we've put a platform together that can contain all of that data, can do the analysis at that kind of scale. And so it's really by working with other companies and other partners that we can enable that as well. So that's what I'm really excited about over the next few years.
I'm on mute. Thank you. Thanks, Peter. Craig, let's go to you, and then we'll have Matt clean up.
Thank you, Barbara. Well, yeah, we are, to your point, Peter, we are in very exciting times. It's been interesting for me to be on the forefront of this virtualization process where we are that digital twin that we're creating, and it always leaves me with an appreciation of the human mind when you really think about it, is the amount of energy and infrastructure and equipment and everything else that we have to assemble collectively to mimic what we have in the human mind. Is just it really, when you look at it in that perspective, it pays, it shows you how far behind we are in developing these things, because we all have one of these inside of our own heads, and it takes a utility, enormous energy and resources to reconstruct something that's a rudimentary representation of that.
Yeah, great comment, Craig. Matt, over to you.
I would just say, one of the things I continue to look for is, we're not going to light our scan probably every distribution line because we have 250,000 miles of them. Although we have companies that would love to do that for us. We're looking for all feeds that we can process. So whether it's Earth observation, mobile LiDAR, our own, vehicle cameras, anything, right? State-run projects, anything that can get us closer to that digital twin for the entire system on the distribution side. It's going to take all that to get there.
Yeah, I think I'm reminded when you said that, Matt, about for me, we all know one person's noise is another person's signal. So I'm sure there are people out there collecting data where those power lines are actually just getting in the way of the signal that they want to collect. And so their noise is your signal. So that if we had a tool that could in fact integrate and capture this, it would be quite powerful. Listen, let me thank each of the panelists and the participants who asked questions. If we didn't get to anyone, blame me, nobody else. Thank you for your time. I'm really excited about the future and appreciate just the candor with which you guys came in and presented both challenges and opportunities. Gavin, I'll turn it back to you. Thank you for indulging us for a few minutes after our allotted time.